What's up, eco-nerdlings? In this podcast, we're going to be reviewing climate and weather before we move into our unit in air pollution. So I want you guys to open up your journals and write all of these questions down. By the end of all of the podcasts for this unit, you should be able to answer all of the questions that are posed over the next 3 slides. So please make sure you pause, take the time to write them down, and as we get to the topic of the question, make sure you write down the answers. Alright, so as a review for climate and weather, you need to make sure you know the difference between the two. Weather is the condition in an atmosphere at a given place and time. So we live in Texas in the Houston area, so a weather report might say it is 110 degrees with 100% humidity, no wind, and no cloud cover. So as I just kind of got through explaining with my example, weather can include temperature, atmospheric pressure, precipitation, cloudiness, humidity, as well as wind. Climate, on the other hand, is the average weather conditions over a period of years in one place. So we might say that climate over a period of years in one place might be, higher climates in Texas than there are in Alaska. So the climate's going to differ. Two of the most important factors for climate are going to be latitude and elevation, and those are what help us to determine climates in different areas. Typically, the closer to the equator, we're going to have much more hot climates. As we get to the 2 poles, we're going to have much lower climates because they're going to be further away from direct sunlight. So temperatures in those climates, or in those areas, are going to be much lower than they would be around the equator. So solar energy and global air circulation. Basically, that's what's responsible for distributing heat. We have global air circulation, and it's affected by the uneven heating by the Earth's surface from solar energy, seasonal changes in temperature, as well as precipitation. So looking at this little graphic right here, it's basically showing you the different seasons, and it's showing you the position of Earth relative to the sun. So as we all know by now, or at least you should know by now, the Earth revolves around the sun, and it's tilted. So whenever it's tilted towards the sun, that's when we experience summer. When it tilts away from the sun, that's when we experience winter. So while it is winter in the northern hemisphere, it will be summer in the southern hemisphere, and vice versa. So by definition, air pressure is pressure exerted by the weight of Earth's atmosphere. At sea level, the air pressure is equal to 14.69 pounds per square inch, or ppsi, which is an abbreviation you might have seen before. That's something you might see in tires of a car or tires of a bike. Whenever you look and it says, it needs to be filled to whatever it is, and you see the little ppsi afterwards, that's what it's referring to as the air pressure. So the instrument that's used to measure air pressure is called a barometer. So pressure gradient. This changes from high to low, and on a map there's actually an arrow to show this. A higher pressure gradient means that there's going to be stronger winds, and typically the isobars on a weather map would be drawn closer together to represent this. So the cause. How is wind formed? Well, wind is caused by the pressure gradient force. High pressure means more air, and low pressure means less air. The air moves from high to low, and this causes wind. So the Coriolis effect is actually a result of wind. It forces the atmosphere created by the rotation of the Earth on its axis that deflect winds to the right in the northern hemisphere and to the left in the southern hemisphere. So the Coriolis effect is the global air circulation, and it's affected by the rotation of the Earth on its axis. So looking right here, we have our westerlies, the northeast trades, the southeast trades, and then the westerlies again. So we also have convection currents that occur. This is something we've spoken about before as well. So just keep in mind that hot air rises, and then as it cools, it's going to sink, it warms up, and then it's going to rise again. So we'll say we're going to start right here. So we have low pressure, and this is going to be our cool, dry air. So the cool, dry air starts to sink. So it falls and it starts to be compressed, and as it happens, it starts to warm. This now becomes warm, dry air. So the warm, dry air flows down, and this creates high pressure. So it flows towards the low pressure, so it goes from high to low pressure, and it flows towards that low pressure down the gradient, and it starts to pick up moisture. So there's a very moist surface that's warmed by the sun. So this moisture is hot, becomes wet, and so that hot, wet air starts to rise. As it rises, it expands. As it expands, it starts to cool, so eventually it's going to condense and precipitation will occur. And then heat is released, radiates to space, and we kind of start the whole process over again. So heat and moisture are distributed over the Earth's surface by vertical currents, which form 6 giant convection cells at different latitudes. So looking at right here, these are talking about the 6 different convection cells and where they are in latitudes. So we're going to have some in the northern, some in the southern, we're going to have some near the equator, and all of them are going to have these convection cells that are occurring where the hot air rises and then the cold air starts to sink. It picks up moisture, so this is basically a cycle that happens over and over and over and over. So we have friction. This is a combination of the pressure gradient force and the Coriolis effect. Friction at the Earth's surface causes winds to turn a little, and the friction runs parallel to the isobar. We have upper level flow. There is little friction up in the upper troposphere driving surface features. So for example, during big thunderstorms, the wind in the upper level will tell which way the thunderstorm is going to be moving. So we have cyclones. These are also called hurricanes in the Atlantic, and they're called typhoons in the Pacific. These are very violent storms that form over warm ocean waters and can pass over coastal land. So we've experienced a couple of hurricanes in the area that we live, in the Galveston area. The most recent one was Hurricane Ike, so most of you should probably remember that. It has giant rotating storms with winds of at least 74 miles per hour. And the most powerful ones have winds at velocities that are greater than 155 miles per hour. We also have anticyclones. This is an extensive system of winds that are spiraling outward from a high-pressure center, circling clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So Hadley cells. Wind that rises at the equator. And as the air rises, it spreads out to the north and the south, and then it sinks at about 30 degrees. This is why most of the world's deserts are found at about 30 degrees. These are called the horse latitudes because early settlers would get stuck here in their boats and they couldn't move. So all they could think of was, well, we need to get rid of weight so we can get on our way. So eventually they would throw the poor little horses overboard to lighten the load and get moving again. So that's why they call it the horse latitudes. And then in convection cells, we have ocean water that transfers heat to the atmosphere, especially near the very hot equator regions. This creates convection cells that transport heat as well as water from one area to another. And the resulting convection cells circulate air, heat, and moisture both vertically from place to place in the troposphere, leading to different climates as well as patterns of vegetation. And we also have polar cells. Air rises at approximately 60 degrees and it floats south, and then it sinks around 30 degrees both to the north and to the south. And then sea breezes. These are ocean to land breezes that occur during the day. Opposite is a land breeze, and these are land to ocean breezes that occur at night. And then we have valley breezes. As wind blows from the plains into a valley between two mountains, the wind has to be diverted into a smaller area. This actually causes high winds to form through the valleys. And then we have mountain breezes. This is when cool air is coming from the top of the mountain and it sinks on the eastern slope. This is causing an increased wind at the mountain. So polar versus tropical, air masses and storms. The atmosphere has 3 prevailing winds. Prevailing winds that blow from the northeast near the North Pole or from the southeast near the South Pole are called polar easterlies. We also have tropical winds that blow from the northeast in the northern hemisphere and from the southeast in the southern hemisphere, and these are called the trade winds. So we have continental versus maritime. The continental fronts are generally cool and dry, whereas the maritime fronts, which maritime means ocean, are generally warm and moist. When these two air masses converge, it usually results in rain. So warm fronts, you hear a lot on the weather, we have a warm front coming, we have a cold front coming. So what is that? Well, the boundary between an advancing warm air mass and a cooler one is replacing. So because warm air is less dense than cool air, an advancing warm front will rise over the mass of the cool air. In a cool front, the leading edge of an advancing air mass of cold air. Because the cool air is more dense than the warm air, an advancing cold front stays close to the ground and it wedges underneath less dense warmer air. A cold front produces rapidly moving towering clouds called thunderheads. And then we also have a stationary front. A stationary front is a transitional zone between two nearly stationary air masses of different densities. And then we have an occluded front. An occluded front is the air front established when a cold front occludes, meaning it prevents the passage of a warm front. So here are the ocean currents and how they're distributing heat as well as nutrients. So right here, you see rays of sunlight that penetrate the lower atmosphere and they start to warm Earth's surface. Right here, you see that Earth's surface absorbs much of the incoming solar radiation and it degrades it to longer wavelength infrared radiation, which then rises into the lower atmosphere. And then some of this infrared radiation actually escapes into space as heat, and some of it is absorbed by molecules of greenhouse gases and emitted as even longer wavelength infrared radiation, which starts to warm the lower atmosphere. As concentrations of greenhouse gases rise, their molecules absorb and emit more infrared radiation, which adds more heat to the lower atmosphere. So distributing heat and nutrients for our ocean currents. In global warming, that's something that you guys have probably heard a lot about. So there's considerable scientific evidence as well as climate models that indicate that large inputs of greenhouse gases from anthropogenic activities, meaning human activities, into the troposphere can enhance the natural greenhouse gas effect, and it can change the Earth's climate in your lifetime. So what's the structure and science of the atmosphere? Well, the atmosphere consists of several layers with different temperatures, pressures, and compositions that they're categorized by. So we have our troposphere, we have our stratosphere, which has the ozone layer, the mesosphere, the thermosphere. We also have what we call the exosphere. So the atmosphere's innermost layer is called the troposphere. It's composed mostly of nitrogen and oxygen, with very small amounts of water vapor as well as carbon dioxide. The ozone is the atmosphere's second layer in the stratosphere, and it filters out most of the sun's UV radiation that's harmful to us and most other species as well. So in the troposphere, 75% of the mass of the atmosphere is actually composed of the troposphere. It extends from 0 to about 11 miles in altitude, and again, it's composed of 78% nitrogen and 21% oxygen. This is the location of Earth's weather, and temperatures decrease with altitude until the next layer is reached, where there's a sudden rise in temperature. So the next layer is called the stratosphere. The stratosphere extends from 11 miles to 30 miles in altitude. It's typically very calm here. Temperatures increase with the altitude, and it contains 1,000 times the ozone of the rest of the atmosphere. And ozone forms in an equilibrium reaction when oxygen is converted to ozone by lightning or sunlight. 99% of ultraviolet radiation, especially the UVB rays, are absorbed by the stratosphere. Then we have our mesosphere. This occurs between 30 to 50 miles in altitude, and the temperature here decreases with increasing latitude. Then we have our thermosphere. This occurs between 50 to 75 miles in altitude, and the temperatures here increase with increasing altitude, and the temperatures there get extremely high. This is probably something you see if you ever watched Apollo 13 or any of the other shows that, show them coming into the atmosphere and everything turns red and it's very fiery. That would be the thermosphere because it's extremely, extremely hot. Well, I hope you enjoyed this video lecture and you learned a little bit more about climate versus weather and some of the contributing factors to those. If you'd like to rewatch this video or any others, you can visit my website at www.nerdlingscience.com. Well, this is the Queen Nerdling signing off for now. Stay nerdy till next time.